Hello there, Mr. Sutton here, bringing you the Algebra 2 2-1 lesson on transformations of quadratic functions. For Algebra 2, this is a two-part lesson. For the honors, this is one part. Here's what we're doing. We're going to be describing and graphing transformations of quadratic functions. So we've already done transformations with absolute value and linear functions. We're just applying that to quadratics now. And we're also going to be writing functions that represent these transformations of quadratic functions. So let's get to it. To start things off here, we're going to give you the function f of x equals x squared. Pause the video and take a moment and use this table with these x values from -2 to 2 to see if you can graph this out. And then figure out the domain and range based off of that. Give it a shot. All right, so going through and getting each of these, -2 squared is going to be +4. -1 squared is 1. 0 squared is 0, and then 1 squared is 1, and 2 squared is 4. So putting those on my graph, we've got -2, 4 right here. Here's 1, -1, 1, 0, 0, 1, 1, and up here we have 2, 4. Connecting those dots, we get this nice little curve here. So in general, something with an x squared, that is called a quadratic function. And you might be thinking, well, quad usually means 4, but the quad they're talking about is like a college quad, which is a square. So it's talking about this squared piece, if you were ever wondering about the name. And the shape that we get here, we can think of this as a U shape. It's kind of like the absolute value has a V shape. It's very similar. But we also call this specific shape a parabola. So it's good to know both words there. Now, for the domain of this, we see that we're going forever to the left and forever to the right. And in fact, you can plug in any x value you want and square it, and you'll get a real number back. So this has a domain of all reals, just like the absolute value and the linear functions. But we also see for now the range, the y values we can get back. We can't get back any of the negative values here. The lowest we can go is 0, at least with the parent function here, and we can get all the positive numbers. So our range, just like the absolute value, is going to have y greater than or equal to 0. So now one key feature of these types of functions here is that unlike the linear functions, but similar to the absolute value, we see that we've got this turnaround point. We call that the vertex, the point at which the parabola reverses directions. And there's actually a specific form of a parabola called the vertex form. And here it is. Y equals, or f of x equals, a times x minus h squared plus k. This form is kind of like the form that you were used to graphing the absolute values in, where you could do transformations of the function by, changing the multiplier outside the function and adding and subtracting things inside and outside. So all the transformations we did with absolute value, we can do with parabolas or quadratics in this form. So just a little review of, and this also gives us the vertex, by the way. That's why we call this the vertex form, because this h and this k are the vertex that we can pick right out of there. So just a little review now of transformations. Remember that there was inside and outside changes that we could do to a function. And by inside in this instance, we mean inside this squared parentheses. That is the thing being squared. Outside is outside the squared stuff. So remember that inside changes are horizontal. They affect the left-right. And they are inverse of how they appear. They behave oppositely from how they appear to behave. And then the outside changes, things outside the square now, are going to be your up-down vertical changes. And they're going to do exactly what they appear to be doing. So with that in mind, let's apply some of these transformations. For our first example now, we're going to describe the transformation of x squared that this g function is performing, and then we're going to graph it. So what are we doing here with this +4 inside and this -1 outside? Well, remember that inside changes are left, right, and behave oppositely, inversely of what they look like. So adding 4 to the x inside really means we're subtracting 4, so we're shifting everything to the left 4. This -1 outside is a vertical change, and it's exactly what it looks like. We're just shifting down by 1. So we have it then a translation left 4 and down 1. So we'll start by writing our parent table. That's the one you generated in the beginning. with the x squared, so negative 2 through 2, giving us 4, 1, 0, 1, and 4. And then we'll just come up with some rules for x and y based off of what we said here. So you probably know enough to take it the next step here. See if you can figure out the rules for x, y. Pause the video and see if you can then graph this thing out. All right, so we've got left 4. That means we need to do x minus 4. And then down 1 means we're going to be doing y minus 1. So we'll subtract 4 from all the x values. So that's going to be negative 6, negative 5, negative 4, negative 3, and finally negative 2. That's all our new x values. And then for the y values, we're going to be doing, let's see, 4 minus 1 is 3, 1 minus 1 is 0, then we've got negative 1. And then these two y values are the same, so we get the same kind of going in the opposite direction, so 0 and 3. Let's put on our xy axis now and graph these. So we have negative 6 comma 3 right up here. And then we have negative 5, 0 is right here. Negative 4, negative 1 down here. And then negative 3, 0, and negative 2, 3. And then graph the parabola through that. For this next example, we're going to be transforming x squared into negative 1/2 x squared. So pause the video and see if you can figure out what this transformation is doing and come up with the new x and y rules and then graph it. All right, let's see how that went. So because we've got stuff happening outside the function on this one, these are all going to be vertical changes. A negation here gives us a reflection, so a vertical reflection. Multiplying by 1/2 is going to give us a stretch or a shrink, in this case a shrink because it's less than 1. So we've got a vertical reflection and shrink. Now if this stuff had happened inside the function, that would have been a horizontal reflection, and multiplying by 1/2 inside would have given us a stretch instead of a shrink. Remember, stuff is inverse of what it looks like if it happens on the inside. So going back now, we've got our parent table. Again, for x squared, we've got these 5 points that work very well. One reason I like these 5 points is because they include the vertex in them. The vertex is probably the most important part of the parabola. If you graph a parabola without showing the vertex, it's not really going to have that nice parabola shape to it. So now what does the G rule look like for each of the x and the y's here? We didn't do anything horizontally, so x is still just going to be x. Nothing's changing with these x values. Vertically, though, we reflected and shrunk things. We're essentially multiplying the y values by negative 1/2 here. So negative 1/2 y. Let me go back and write my x values now. We've just got all the original x values, negative 2, negative 1, 0, 1, and 2. For the y values, though, we're multiplying all of these y values by negative 1/2. So 4 times negative 1/2 is negative 2. Then we have negative 1/2. 0 is still 0, negative 1/2, and 4 times negative 1/2 is negative 2. One thing that is kind of worth noting here, and you might have noticed this also when we did the absolute value transformations, is that this turnaround spot at 0, 0, because 0 is unaffected by multiplication, this spot is unaffected by reflections and stretches and shrinks. It still stays in the same spot. That's part of the reason the vertex form of a parabola actually works, because if you just look at the stuff that's happening in terms of plus and minus inside and outside the function, that's the only thing that's going to change these 0 values. Multiplying, all the shifting and reflecting doesn't do anything to it. So now let's put this on a graph. We've got negative 2 right there. And then we have negative 1, negative 1/2 is right about here. 0, 0, 1 comma negative 1/2, and 2 comma negative 2. And this actually should be a negative 2 here. There we go. That was an easy fix. Now let's put it at 2 comma negative 2. I mean, negative 2 comma negative 2 was a point, but we don't need to put the same point twice. So let's now draw the parabola through those. Whee! And there we go. So just to kind of do a sanity check here, did we reflect this vertically? We did. Did we shrink it horizontally? It's kind of hard to tell with parabolas unless you look at where the points started and where they ended up. But all of these points moved half the distance to the x-axis. So that's what a shrink is going to look like with these. Now, if you are doing the Algebra 2 non-honors, then this is the end of part 1 for you. Feel free to stop here and do whatever homework assignment you need to do. If you are doing the honors version, then we're just going to keep on going. So if you're doing the non-honors Algebra 2, then welcome back to part 2 of our presentation. In this one, we're going to be writing rules for these quadratic transformations. If you're honors, then hey, you never left, so let's just keep going. So they want us to write a rule described by the transformations that they've listed here for this f function, which in this case is x squared, but it's not necessarily always going to have to be just x squared. And then they want us, based off of this, to identify the vertex. So when you're doing these, my advice, just like we did them with the absolute value and everything else, is if there's multiple transformations happening, do one of them at a time. Create a new function for each transformation just so you don't lose anything. And I also recommend kind of using the, do like a general, like big picture sort of transformation of the f function before you actually plug anything in. So for example, like vertical stretch by a factor of 2. Okay, what would that look like with the f function? Well, it's vertical, so it would be outside. Stretching means we're multiplying. So I could write a g function that would equal 2 times f of x. And then I could go ahead and just replace the f function with this x squared here. And this is a function that now does this, but with a vertical stretch of 2. So pause the video and see if you can go the rest of the way with these transformations to get to the final function. And then we'll bring it together again before we talk about the vertex. All right, so the next thing they wanted us to do was a reflection. Now, actually, the reflection and the stretch could happen at the same time, but let's just do one at a time. So if we're reflecting in the y-axis, that's a left-right reflection. That means I'm going to have to change the input to the g function to be a negative x. So I'm going to write a new function, h, that's going to equal g of negative x. And since the g function is just 2 times x squared, this is 2 times negative x, quantity squared. And you could simplify this. When you take negative x and multiply by itself, you just get positive x squared. So the g function and the h function, that actually makes no difference. And that does kind of make sense for a parabola. If you're on the y-axis, reflecting it over the y-axis, you're going to get the same shape because it's symmetrical. All right, so we've got one more to do. That's a translation of 3 units down. So I'm going to write another function. I don't like using I as a function, so I'm going to use j instead. J of x, I'm going to call that h of x, and then 3 units down, I'm going to have to subtract 3 from the h function. So h of x minus 3. And since the h of x function is just 2x squared, that's just 2x squared minus 3. So that's what my transformed function looks like. Now this is in vertex form. There's kind of like an x minus 0 that we're not writing here, but you could think of this as x minus 0 quantity squared. So pause the video for a little bit and see if you can figure out the vertex based off of this. All right, since we're doing x minus 0, that means that 0 is the x value of our vertex. Subtracting 3 outside the squared stuff means we have a negative 3 for the y value. So this is going to be a vertex of 0, negative 3. We're going to do one more example of writing rules of quadratics here based on transformations. In this one, you'll notice we didn't just give you like plain old boring x squared. We gave you a little bit more. But still, the principles are going to be the same in how we apply these things. So pause the video, see if you can give this one a shot, write the new function, and see if you can find the vertex based off of that. All right, let's see how that went. So we have a translation 2 units up. That means that my g of function I'm going to write to do this has to take the f function and add 2 to that. So that's just going to be all of this x minus 2 squared minus 6 stuff plus 2. And all that gets affected is this minus 6 out here. Adding 2 to that just makes that a minus 4. So not a huge change there, but we're not looking for big world changes here. The next thing they needed was a reflection in the x-axis. Since this is a vertical up-down kind of change if we're going over the x-axis, we need to put a negative outside whatever that we're changing. So I'm going to write the h function now, and I'm going to call that negative g of x. That negative goes outside. G of x is all of this x minus 2 squared minus 4 stuff. So I'm just going to put a negative outside of all of that. But I do have to distribute this now. So this is going to be negative x minus 2 quantity squared. And then minus minus gives us a plus 4, which is going to be important. Now, if I want to pick the vertex out of this, this is in vertex form. There's actually two other forms of a parabola that we're going to see, of a quadratic, but we're not there yet. So the thing being subtracted inside, again, that's the x value of the vertex. This minus 2 inside means we have a positive 2 for the x value of the vertex. Remember, inside changes are inverse of what they look like. And then the plus 4 really is a 4 for the y value. So 2 comma 4 is going to be our vertex. So that's it for this lesson on quadratic transformations. Hopefully, upon reflection, this was a transformative experience for you. Till next time, Mr. Sutton signing off.